So kind of cross topic, maybe completely new topic, at least according to the other title. So I will try to give you a little bit of introduction about what I'm doing. So let's start just with a brief sort of advertisement just to let you know who I am and where I work. So I work at CERN, you know, maybe this place in Geneva where we have the accelerator where we study proton-proton collision, but essentially we have a quantum technology initiative within CERN that is divided in 4 main competence center. I'm coordinating the one on hybrid computing and algorithms. And then we have people working on quantum technology platforms, so more on the hardware side. And then we have an initiative about quantum network and communication, so quantum key distribution and quantum sensors. And then there is a specific initiative for training and collaboration with industries and academic center. Also, for me, it was not an easy task to better understand how to structure the talk. So I decided to go with this kind of main topics. I will try to motivate, at least to give you a bit of introduction about this quantum computing for those of you who are not familiar. It will be very short, so if you are already aware of the topic, it will last not so much. And then I want to give you ideas about what is a quantum algorithms and what are the connections with machine learning. And then I want to give you some example of realistic application where quantum algorithms and quantum machine learning is applied in high energy physics. And then we'll try to summarize and go for lunch. So let's try to motivate why we use quantum technology. And this is the same motivation I use in every kind of talk, in particular with CERN Council to ask for funding. So it should work. Let's see. So on the theoretical side, at least on the physics side, we have some strong motivation. And what are motivation are theoretical challenges. So theoretical challenges from high energy physics are the fact that when we have proton-proton collision here, we start already having some kind of trouble in the sense that we know exactly what is the proton structure, but it's essentially a quantum field theory problem. So we don't know exactly how to encode this in an algorithm, essentially, because we don't know exactly how the physics works. And in particular, what is happening between the collision, so when we smash together the protons, and the final product that essentially we measure and we experimentally measure at our experiment, is somehow a collection of very complicated theories that goes together from the more Lagrangian or quantum field theory approach to the experimental setting. So from the electronics point of view. And in the middle, we have different things. In particular, we have some strange phases that is called quark-gluon plasma when we have a high density of proton and that is mashed together. And we have a very, let's say, complicated effort in describing and code this in our computational paradigm. So essentially, we want to encode the quantum chromodynamics, and this is very complicated, somehow impossible. There are different initiatives and ideas to do that, but it's very complicated, and we don't know exactly how from this strange phase of matter we can get out of our particles like pions, kaons, and Hebbier particles. So essentially, we have a real challenge in terms of theoretical challenges that go from real-time dynamics of this EV ion collision and scattering quenches and so on. But then from the computing side, from the algorithm side, this translates into a computational challenge. I'm still talking about classical computation. Now, since we're talking about quantum, I have to make this distinction between classical, or if you want, classical computation or quantum computation. And the plot that you see here, it's a real estimation of computing resources for the Atlas experiment, one of the 2 biggest experiments at CERN. And you see you have a conservative and aggressive R&D proposal for the computation, and this is the annual CPU consumption, so just the computing power for this experiment. And as you can see here, we are going far beyond what is the current availability of tools and computation. So from the theoretical challenge, we are translating this in a computational challenge for what is the development of LHC. We are going to maybe build a bigger one, but at least we are going to increase the energy of the current accelerator. So everything that relies on simulation and analysis will be much heavier. Why is that? Because everything we measure, it's been simulated before. And so we need to do this very, very well. Specifically for quantum technologies and quantum computing and algorithm, we have also some motivation specifically for that. So here you can see a kind of sketch of our pipeline in terms of processing. So we start writing Lagrangian on the whiteboard, and then we have to define something that we essentially measure at the experiment. And in the middle, you can put very interesting and fascinating things from the hard process that you usually draw with Feynman diagrams. But then you have to take into account the showering of the particles, the effect of the hadronization, and the effect of the detectors. All of these effects, of course, are based on quantum field theory. And so we have already some proof that we have already quantum effect in that. So starting from entanglement, interference effect, until very recently, and a very interesting direction of measuring Bell inequalities out of energy physics data. So we have quantum motivation for that. So the idea is that on the algorithm side, we want to utilize information and correlation that are inherent in our energy physics data. It's not just that. Quantum computing in general received in this recent year a lot of money because there are potential applications in many fields, also beyond energy physics. We are just a very small community within the total budget of money spent on this topic. You can see here many other applied research from batteries, material design, and also on the business operations side, on the financial services and manufacturing. Which one will be the best one to show what is called quantum utility or quantum advantage is still under discussion. Of course, everything that has to deal with quantum effect, so chemistry, material design, and so on, it's a very good candidate. But also we know very well that we have quantum algorithm that can accelerate mathematical subroutine also in machine learning and artificial intelligence. Just a very pedagogical slide. I'm sorry if you know already this, but I just wanted to set the stage so we are on the same page. Basic idea of quantum computing is just shifting from a traditional encoding of bit in the classical unit of information on the classical side, so deterministic. So whatever we do with machine learning is a deterministic kind of information. You have 0 and 1. And what we are trying to do with quantum computing is to explore the complex space. So we are working in the Hilbert space. And so we use the qubit or quantum bit of information that is characterized by quantum properties like superposition, entanglement, and interference. So for one single qubit, you can exploit the superposition. Essentially, the state of your qubit is described as a linear combination of the state 0 and 1 in the computational basis, meaning that you can define with one qubit the position within this block sphere, so this unital sphere. And going beyond 1 qubit start to be very interesting because then you can use interference and entanglement effect. And in a sense, the operation that we apply on qubit in terms of computing are essentially matrix operations. So we need to rotate this qubit to apply some operation, and the rotation are usually described by unitary operation, of course. And traditionally, we use the Pauli gate notation. So you have sigma x, y, and z, or you can use Adamar gate that create a superposition state. Again, starting with qubit to qubit, the things becomes more interesting. And here you can start differentiating what is usually described as probabilistic computing with respect to quantum computing. There is a strong, of course, difference, even if, of course, quantum mechanics is probabilistic theory. Just for understanding, so here we have a couple of examples of effectively an operation that create an entangled state. So you have the C0 operation and a C-wide. And in general, we can create algorithms applying this multi-qubit operation that should create universal gate set. And what is an algorithm? Essentially, an algorithm is described by, at least for gate-based quantum computing, as a sequence of this unitary operation. So you apply in sequence all of this gate, and you can entangle more and more qubits together to create something that should provide you some kind of interesting result. Of course, in the end, you have to apply the measurement operation. And usually we say that this is where the magic finish, in the sense that whatever you can do along the quantum algorithms, exploit all the properties of quantum mechanics, and then you define your operation, then you can collect the information. So in the end, out of this circuit, you will have again a classical bit string operation out of quantum computing. And of course, here start also the hardware challenge in terms of quantum computation, so that everything that we, let's say, write on the whiteboard that should happen within the hardware should work very fast, in the sense that then on the hardware you have to take into account noise and all the coherence effect. Okay, again, we have different, if you want, paradigms for quantum computing. The base one, or the one that I know more because I'm working on it, is the gate-based quantum computing. Again, it's a sequence of qubit and then a sequence of operation that you can solve with an algorithms. And usually it's really implementation of any kind of unitary transformation. And this sometimes is seen as a sort of restriction, but we can eventually discuss about this. And then you have other two paradigms. One of it's called analog quantum simulator. So usually here the problem is embedded into a graph, and you use some kind of dynamic qubit positioning where you don't have any kind of, you have pure control of local qubit operation, but you consider the system as a whole system. And usually this is the typical paradigm for trap ions and atoms. And then you have quantum annihilers, where the problem is embedded in a sort of restricted Boltzmann machine, usually that you can solve using quadratic unconstrained binary optimization. And one of the most famous company in this regime is called D-Wave from Canada. Okay, so let's try to dig a little bit more into quantum algorithms. So I want to make the things easy, but actually it's not. So there is a very complication of how to define quantum algorithms. Of course, maybe the image is blurred, but it's on purpose because I want to go into the details. But just to give you the idea of the complex setting and correlation between all of these algorithms. But why I put this picture here? Because I want to mention that we have different paradigms for quantum computation on the hardware side, but importantly also on algorithm point of view. We will see that we have approaches that are going into more gate-based quantum computing, into annealer, but also into what we can actually do now with what we call noisy intermediate scale quantum device, or NISQ, if you want, with respect to what we think we can do in the near future that is called fault-tolerant quantum computation. In the end, as you may know very well, the performance or theoretical guarantees of an algorithms, in particular on the quantum algorithms, is based on the fact that you can connect different components about the algorithms. And of course, you have to give some kind of theoretical guarantees about any kind of speed up or complexity. Unfortunately, you cannot do this for all of the algorithms, in particular for machine learning type or variational type of algorithms, also in the quantum setting. So what we have now and what we are working essentially now is on this part, on the bottom right part, the gray part, that is called NISQ, or variational quantum algorithms. And I will try to give you a better explanation about that. But the community, of course, is more concentrated in what can be done in what is called fault-tolerant quantum computing. So essentially, the most famous algorithm is the Shor algorithms, that usually is used to scare people about their bank account and so on. But essentially, this is a real fault-tolerant quantum computer, in the sense that even with the best resource estimation we can get today, we need more than 100,000 of logical qubits, which are very complicated to attain in the next years. And those are part of fault-tolerant quantum computing, and in particular, it's important to know that for this kind of algorithm, we have theoretical guarantees and complexity understanding of how they work. Okay, so in general, a quantum algorithm should work like this, and this is essentially true for, again, fault-tolerant quantum computer. So you initialize your qubit states, usually in the 0 state, which is a computational base. Then usually in a quantum algorithms create a superposition of all possible states, because you want to exploit all the properties of quantum systems. And this is done with a combination of Hadamard gate. And then usually you add what is called ancillary qubit to sometimes post-process the information, or to really park the information in some point of the circuit that you can collect. And then you define your big unitary operation that is usually called black box or oracle, if you want. And this is where the potential of quantum algorithms rely usually. And in particular for one of the algorithms that is called the Grover's algorithms that usually introduce like an algorithm that allows you to get a quadratic speed up for search in an unconstrained database, give you what is called a quadratic speed up because the number of times you query the algorithms is quadratic, better than the classical one. And then you have a sequence of operation that is very well described here. And then you can collect the result at the end of the circuit. And for this kind of algorithm, usually you need, this is what you find in the textbooks, but then when you want to apply on to run this on real devices, there are a couple of bottlenecks, usually the input and the output, which are really a bottleneck for an algorithm point of view. The input is a bottleneck because you have to prepare this oracle, and sometimes you need the classical preparation, either to process this oracle, but also if it is a quantum algorithm that deal with data, which usually we work with, you have to prepare the circuit to encode the data. And this classical preparation usually burned your theoretical advantage. And also you have a bottleneck in the output because again, you measure once and then you have to collect the output of this circuit. Yeah, sure. So again, this H tensor N is the creation of Hadamard state. So you have a superposition of all possible state of your register. So you have a superposition of all the states. So you can assess theoretical all the state in the circuit. And this X gate usually is the classical not gate in the classical circuit. So essentially you go from state 0 to state 1 in the block sphere representation. This oracle is a collection of different gates that prepares your function to evolve as a unitary operation. And then again, usually here in this Grover diffusion, you have some kind of reversible computation. So you want to go back to the origin of the preparation of the state. So here again, you have a series of Hadamard gate, and then here you measure the final state of the circuit. No, yes, they can be implemented. It depends how complex is the unit that you want to implement. Sometimes this is very long in terms of number of gates that you need. So essentially, the Shor's algorithm requires kind of thousands of gates to be implemented. And this goes beyond the current hardware availability in the sense that once you go beyond what is the typical time to the coherence for the hardware, then you lose all the quantum properties of the system because essentially the qubit collapses in the ground state. Then essentially it's a classical bit, it's not a qubit anymore. And so as a kind of workaround, we have variational algorithms that are the one that people are working much more in these days. How does it work? Essentially, you have, again, this preparation of the qubit register. And then instead of having an oracle, essentially what you do is very similar to what you do with neural networks. So you have a parameterized circuit where the parameter is the rotation of the qubit. So essentially you encode your data in some way in the amplitude of the state of your qubit, and then you define rotation as a function of some parameters that you want to optimize during the optimization of the algorithms. Usually they are called variational algorithms or hybrid algorithms because you have to match quantum computer and the classical computer because you run your algorithms for one time here where you had different number of layers according to the expressivity of the circuit that you want to implement. Then you define the way you want to measure the circuit in the end. So you can define the observables in terms of quantum mechanics of the circuit. And then the circuit gives you a bit string that represents the expectation value given that circuit. So what you do then, you give the output to a classical optimizer that will update the weight of the circuit for you. And that is why it's called hybrid, because you have a continuous iteration between the quantum and the classical computation. So the quantum evolves the unitary circuit, give you an output, and then the classical circuit optimize the weight for you. So essentially you rerun the circuit with a different weight of the quantum circuit as well. And then you iterate until you get to the final solution. So you have to implement a loss function like you do in classical neural network, and we will see what are the drawbacks in this sense that are, of course, greater than what you can have in standard machine learning optimization. Again, here, You have the classical initialization, as I told you. Also, this is a very open area of research, the way you initialize the quantum circuit, because under some condition, the circuit cannot be trained, or with other condition, a circuit is easy to find the correct solution. And then you see here the flow, how does it work? So you collect the output from the quantum circuit, you post-process this with a classical computation that give you the new theta to optimize, and again, until this reach the convergence. And so this is one of the main reasons why you cannot give complexity or computational guarantees for this kind of algorithm. So usually you have heuristics, and so usually they work because the circuit works, but you don't know this in advance, of course. So what I want to say is that I will focus mainly on these variational quantum algorithms, in the sense that I will try to give you motivation about the pros and cons of these approaches. But as usually, so the quantum machine learning, so we go into the topic of quantum machine learning, it's really taken a parameterized quantum circuit or variational quantum circuit, and then you have to add the data encoding layer, and then you have to encode this in a cost data dependence. So again, the loss function is obtained by classical processing and measurement. And overall, I mean, from mathematical perspective, the real object that we want to care about is this loss function that can be described here in the mathematical formulation of the trace of this density operator that give you the encoding of the data times this unitary operation of a quantum circuit. So you have U dagger, U where O is the observable of the last layer of the circuit, and U is your probe, is the way you define your variational quantum circuit, is related to your ability to define a good circuit. Is like in neural net, is the ability to give you the right architecture to find the solution for the problem. So our goal is really to solve and let the quantum computer to solve this effectively. Those are two different objects. The rho is essentially a layer of encoding the No, it's just a sequence of Pauli strings, for example, that you can put at the end of the circuit. Usually use the sigma Z Pauli string, but you can have a combination of this. And so essentially, one of the motivation naively for use quantum computer is that people usually say, we use the Hilbert space that has like an exponential big feature space, so we are happy to find the solution. And that's a naive motivation. Sometimes it's true, but of course, these give you some constant. The constant is that it's very hard to find a solution in exponential big Hilbert space. Yes. Yes. Yes, because the iteration, so this is the quantum computer that give you expectation value of the parameterized quantum circuit, so you fix the weight. Then the classical computer essentially give you an hint about how to update the weight within the quantum circuit, and then you rerun a quantum circuit with updated weight. So essentially you change the rotation of each gate operation, and then you collect again the solution until you reach convergence, if you can. Once it's trained, means that you find a solution. Okay. That's a good point. So theoretically, no, in the sense that this is the final quantum circuit that should be used for testing. And so then this should run on a quantum computer. But then, as far as I understand, what I remember, you can search the proportional to the square root of the yes. It's a problem. You search what? To destroy your data. You have to reveal your database again. Yes, sometimes. No, those are two different approaches. So those are the standard quantum algorithms, the textbook one that give you all the guarantees. And I mean, on that size is that why sometimes in the Oracle that is in the black box, usually it's hidden a quantum RAM. So the idea is that you can store states without destroying it. So that's one of the idea. But here is that once you have the final weights, this is what you want to run on a quantum computer. Of course, another direction in terms of research is that people are trying to dequantize this circuit so that maybe getting to the right quantum circuit is a problem that is very useful to run on a quantum computer. Maybe we can get a dequantized version of it that can run on classical hardware, FPGA or TPU, and so on and so forth. a possible direction, but originally this should be something that you can run on a quantum device. So now the idea of quantum machine learning and what the community has been done so far is essentially, okay, let's start from ML and then add a Q and then everything should work. I mean, seems to be the case, but we have essentially a very important difference. Just if you look at the flow of information, so in quantum machine learning, we don't have backpropagation. So at the moment, we are not able to calculate the gradients in the way we do in neural networks. So the flow of information is not like in the classical neural network that you go from left to right and then you go back. Actually, we go only in that direction. And so we have a different way to update the parameters. So the training also, it's very different with respect to the classical machine learning. The idea again is that on the quantum side, we have this parameterized quantum circuit. And one of the main, initially one of the main bottleneck that was thought to be the case is that we have to deal only with unitary operations. So people were afraid about the fact that we can only implement a linear operation, which is true, but it's linear in the Hilbert space. And one of the important results that we got a few years ago is that also with quantum neural network, you can prove universality like you do with neural network. So essentially this was solved with a very nice result. But again, machine learning to quantum machine learning, we have this kind of transformation, but we have to keep in mind that the things works very differently with respect to the classical case. Actually, if we want to give a definition of quantum machine learning, it's not just this, but let's say we have a very multicultural community. And when you have this kind of multicultural community, it's becoming very difficult to speak with others in the sense that we speak really different languages. We have people from quantum physics, from learning theory, from information theory and computation. And so usually even we are looking for we are asking different questions to ourselves. And so if you want to work in the field, it's very complicated. If you try to work in a small team, then you have to agree on the language or to research topic. But at the same time, it's very fascinating. We are learning a lot from people coming from different communities and expertise. So it's just an advertisement in case you want to deal with that. And usually the way it works, and I usually make this kind of parallelism about the life cycle of a machine learning model. So usually very naively, you have data preparation, definition, training, testing, interpretation. And actually we do the same also for quantum machine learning, but with the caveat that things are much more complicated in the sense that if you're talking about data preparation in machine learning, you just encode the data in your circuit and that's it. But with quantum machine learning, you have two different kinds of data. Either you use a quantum circuit directly with quantum data, so data coming from quantum experiment, but this is a very small niche of application. If you want to do real quantum machine learning on what we call classical data, you have to come up with a very interesting and efficient way of encode the classical data into quantum state of the circuit. Then you can have model definition. In here we have the same kind of division that you have in machine learning. So you have supervised and supervised learning, reinforcement learning, so on and so forth. And then the training is very different, as we said before. In particular, we have a very kind of strange problem in terms of trainability issue that is called Barren plateau. And we can say that this Barren plateau issue is the causing of the vanishing gradient. So the effect is very similar. In the end, we are not able to train the circuit, but the cause is very complicated. It's very different. Essentially, the dimensionality of the Hilbert space and the way you define your parameterized quantum circuit give you the possibility to be lost essentially in this Hilbert space so that the right solution cannot be found in an efficient or in a reasonable amount of time. And I will give you a little bit of more mathematical context about that. And then of course you have the model testing and the model interpretation. So again, the readout is done with measurement. So this is where you have this kind of phase shift between the quantum mechanics and let's say the classical one, in the sense that once you measure the circuit, you get finally a bit string. So again, theoretically, we know that the way we measure the things, we get the probability of the circuit by tracing our parameterized quantum circuit times the density matrix of the encoded data. But in practice, with a quantum computer, what we do is a counting experiment. So essentially, we measure every time we destroy the quantum circuit. So in practice, what you have to do is that you have to deal with the statistical precision that we know scaled at the square root of n. That's why for some variational circuit, we have an exponential amount of resources needed to get the right solution. This is why we have sometimes some no-go theorem about that. So I will try to be as fast as possible. But again, also for quantum machine learning, we have explicit and implicit model, like very similar to what we do in classical machine learning. So essentially, we have explicit quantum model that are the variational quantum one, where our cost function is a function of theta. So it's a function of our ability to define your answer function that should span the Hilbert space, or we can even have implicit quantum model that is essentially the quantum version of kernel method that we have in classical machine learning. And we have a kind of combination of the two that is very interesting. It's called data reuploading model. So this is something that is very different to what you can find in a standard approach. So in this case, we have the possibility of encoding the same data multiple times in the quantum circuit. And the result of it is that we can get nonlinear responses, and we can get much more expressibility of the circuit. And this is the model where people prove the universality of quantum machine learning and quantum neural network. So I will skip this part just for sake of time, just to give you the challenge about the parameterized quantum series. So the problem that we are facing now is that, again, we have to find this data embedding and this data handling, which is some kind of additional constraint with respect to the classical case. And then what we call the answer choice, or the definition of the initial parameterized circuit. Essentially, we have to answer two questions. What is the most suitable circuit for this given problem? So we should find a circuit that essentially is able to find the solution. So if you say that this is the accessible space given by your parameterized quantum circuit, this parameterized quantum circuit should match the solution. And so a naive solution is that, why don't you take the full space? And that's a possibility, of course, but then you will see that if you take the full space, you get into trouble because you cannot train anymore the quantum circuit. So you have to find the right balance between the two. A potential ideas, which is very interesting, at least for us from a physics perspective, is try to encode symmetries into your parameterized quantum circuit. And this is very similar to what the community is doing on the classical side of imposing symmetries within your neural network. So for example, in energy physics, there are work that are trying to constrain Lorentz invariance in the neural network to find for classification problem. Then again, the trainability is another possible challenge. So how to update effectively the parameter of the quantum circuit. And then going back to the question, the community is challenged itself in the sense that whatever you do, imagine you have already a solution for all of the three. Then the last point is that, okay, but maybe the circuit that you implemented can be easily simulated on a classical computer. And this is really an important challenge, because if you want to claim that you have a technology on an algorithm that is outperforming with some scale in your classical part, you should be able not to reproduce the result effectively on a classical computer. And this is also an interesting bottleneck. Yes. Because you can restrict the accessible space in a way that you can be able to. Mm-hmm. 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 No. The example of the Lorentz invariant frame was just for energy physics. So if we're looking for classification problem of particles coming from Lorentz invariance, we want to enforce because this is the symmetry of the physics that we are studying. It's not because of reference frames of quantum system. It has nothing to do with that. No. Yeah. Yes.
I have a question about is good news or bad news that is not simulable, or that is simulable in a non-quantum computer and in a classical computer? I'm confused.
Yes. So it's always a point of view, right? If I'm running a startup and I'm looking for funding, and then someone can simulate it classically in my algorithms, that's a problem. On the community itself, what we have seen so far in this year is that we got a lot of advancement in the classical sense, because it's kind of a race. So every time you come up with a new algorithms, that there is always a better solution or better idea about classical algorithm. I discovered yesterday this fascinating topic of algebraic machine learning. And actually I was Googling this morning and I found a paper from a Russian guy about quantum algebraic machine learning, but I don't think it's aligned. It's just a title that maybe it's a click bait, but okay. The title was good, but the content was okay. Okay, no, but it's a very interesting question. Also, what is important is the last point, because then if you want to consider all the metrics within the computational paradigm, you have also maybe some resource efficiency or cost efficiency metrics. So just because we can simulate a loss, so our loss on a classical computer doesn't mean it's practical. I mean, it's something that we have to deal with, some problems and conditions. This is also an open debate. Yes. Okay, I'm trying to run as much as possible. So now I'm trying to show you a few of application of these quantum algorithms, mainly parameterized quantum circuit to energy physics problem, but I give you some kind of context to better appreciate this in the context of machine learning. So just a general idea where we put the quantum algorithms or algorithm in general, everywhere in what is this pipeline. This is what I like most is the pipeline of energy physics, where people coming from theory. So usually they write their Lagrangian, and then what we measure is the probability of a decay process to happen. And this is translated into a number that is called cross-section. That is the result of a very complicated high-dimensional integral calculation. And then also, again, if we want to match what we measure at the experiment level, we have to deal with a very, let's say, faithful generation in terms of data, in terms of experiment simulation. And also we have to deal with feature extraction, because we have to deal with a very high numerosity features problem. So we have different part of the pipeline where we can apply algorithms in general. And this is true also for the machine learning community that we have at CERN the same time. So the first problem that I classify as a theoretical problem, but it's really also a computational problem, is that, again, if we look into the process we are interested in, right? So we want to calculate the cross-section of a process to happen. And usually this is the result of a very complicated integral where we have two parts. One is the physics. So here you have the Feynman diagram, so the process you are interested in, electrodynamics, quantum chromodynamics, whatever you want. And then you have to integrate this with what is called phase space cuts, which is essentially the setting of the experiment. So let's say the angle of the distribution of the particle that you can effectively measure, but also the phase space in terms of energy conservation. So here is where you apply all the physics constraints. And the result of it is an integral that gives you the cross-section of the process. So for a standard experiment like Atlas or CMS, we have 3 billion CPU hours a year spending on this topic as well, because those are very complicated processes. So our naive interpretation is that, is there anything we can do on a quantum algorithm just to accelerate this kind of result? And as usually, we start with toy model. If you want, we don't have the MNIST dataset. So for us, the toy model is a sort of bubble integral that is a very standard Feynman diagram. And the idea is that we want to calculate the integrals of this function that already give you some kind of intuition about the complexity, in the sense that you have some kind of divergences, some pole to deal with, and so on and so forth. It's a very standard one-dimensional function. The idea is that, again, for a quantum algorithm, you have two problems. First, you want to calculate the integral of the function, but before that, you have to encode the function into a quantum computer. So the idea we come up with is that we can use a quantum neural network as a regressor to essentially encode the function into a quantum computer. And then we want to use another algorithm that was used already for other application in finance, for example, to accelerate the integral part. And this quantum algorithm is the quantum amplitude estimation that give you a quadratic speed up, which is not a lot, but for 15 million CPU hours a year, it's already interesting. But why we wanted to use a quantum neural network? Because of the universality reason. The idea is that once you encode the function in this way, you can extract its Fourier representation. And then we have proved that with the Fourier representation given by the quantum circuit, you can apply iteratively the quantum amplitude estimation and then estimate each part of the trigonometric function in a very effective way. And the good part is that we were able to propose this algorithm, but also to test on a real quantum computer. So Those are the result with the points in blue or in red according to different bubble integrams run effectively on a real quantum computer from IBM. So this is something that really works at the moment. Then another application, I will try to go quickly on that, is another application of quantum machine learning. And the idea is that this is a very general problem we are facing in the field. So essentially the way we are doing data analysis and that we have done so far until the discovery of the Higgs boson and so on, is that we have a kind of biased way of looking into the data in the sense that we start with a model. We have the standard model of energy physics. And then we want to see if the data that we are collecting are following or are well described by the standard model. But then you want to look for physics beyond the standard model, what is called beyond standard physics or anomalies with respect to this. And so usually we have a lot of people in the theory department, a lot of people, and usually every day, more or less, they come with a new model beyond the standard model. And so the way you do that analysis with this approach is kind of biased in the sense that every time you have to develop a new model, and then you have to define your excluded region of this new model with respect to the standard model, which is very interesting. But if we want to look really at the total amount of data that we have, this is very time consuming and maybe it's not the best approach to do. So our solution was to come up with a non-biased approach in the sense that we want to look into the data and essentially find an anomalies. This sounds very, very fair and obvious from this point of view, but it was a very game changer for the community that was used to adopt this kind of approach. And this is a very standard approach, for example, on the astrophysics community, because the way they classify the stars is just they look at the stars, their brilliance, their emission, then they do a clustering about them test. So the way we did this is that, so let's look at the data. So we simulate the data with different components of standard model and beyond standard model. And we look at the data and we are looking for anomalies. We look for anomalies. So essentially we approach quantum machine learning model for unsupervised learning. But here, what I want to focus on is more on the preprocessing of the data, because what we have today is a good technology, okay, in terms of quantum computing. But again, the number of qubits to deal with the number of features that we have in the data are not enough. So usually every kind of quantum algorithms has a strong preprocessing part, which is a classical part that do data compression. And so you have to work in the latent space distribution of this. Usually, so you have a classical part, which can be like a quantum, an autoencoder, a variation autoencoder that provide you a compressed representation of the features. And then you are able to encode the features into a quantum computer. So what we did is that we started with a dataset of 300 features and we went back to 4, 8, or 16 according to the number of qubits we wanted to use. And apart from the physics, what we developed is a quantum kernel machine, what is called one-class SVM, that can work very well with anomaly detection. And essentially what we do is compare, again, our result to what is the best classical counterpart, where the best classical counterpart is not the model where you can work directly with the 300 features, but the best classical part that can work with the latent space distribution. So essentially, we compare this with the different neural network, in particular with the classical support vector machine one-class approach. And what you can see here in the top right is what we call the kind of window of quantum advantage, in the sense that the continuous green distribution in this plot that is related to, essentially is the ROC, is a variant of the ROC curve, give you the ability of the model to find an anomalies. And here we have some kind of separation between the quantum part and the classical part. And then what was more important to us is to understand where the quantum circuit is playing a role, because essentially, in terms of power of quantum computing, we know that the interesting part comes when the effect of entanglement play a role, because otherwise, if you can factorize your circuit, then you have a classical algorithm if you don't play with the entanglement. And so what we did is that we did a study of an increasing number of layers for the quantum circuit as a function of entanglement of the circuit. And then what we saw is that under a few layers with a strong entanglement circuit, we get 14 times the performance of the classical one. So in some sense, working from the latent space, this quantum algorithm was working very well. And maybe this is the last slide I want to mention before the conclusion, is that as a sequence of this work, we wanted to ask ourselves, what is the role of the preprocessing with respect to the quantum algorithm itself? And despite the fact that this question kind of naive, because usually one can say, okay, but the performance of quantum algorithms is really dependent on the way you compress the data. What has been done so far in the literature is that everyone that was working with the quantum machine learning was taking a compressed data without wondering how the compress was done. So what we tested is that why don't we do the compression together with the classification or the anomaly detection problem itself? And essentially what we did is that essentially we create a loss function that is a combination of the classical and the quantum setting so that you can compress the dataset and together you can classify the dataset itself. So you're coupling the two tasks together. And maybe it's obvious, but what we prove is that effectively this guided quantum compression was working much better than the two independent set of the classification. And we repeated this experiment not only for this kind of dataset, but with a different problem using graph neural network. So also using a guided graph compressed neural network, and this was a very interesting result. Okay, we work also on generative model, on the quantum setting, so on and so forth. I will go directly to, do I have a few minutes or I should stop on time? 4 minutes. 4 minutes, yes, yeah. I just want to give you just also some kind of open research direction. So quantum mechanics and the way we build quantum algorithms is based on unitary operation. But of course, the reality is much different than that in the sense that when you work on the hardware, you have noise. The system is not a closed system, it's an open quantum system. So what could be very fascinating is to look into non-unitary quantum machine learning. And so for that, we have already a couple of work that are looking into this direction. And the idea is to understand if the noise in some sense can help or accelerate a little bit some performance of the quantum circuit, or at the same time, knowing much better the role of the noise, we can correct the quantum circuit to go back to unitary operation. Yes, here I have some details about bar and plateau connected to dynamical Lie algebra, but I will just pitch the idea. Usually we use MEMA to summarize the things, but essentially the idea of bar and plateau at the beginning was that you can describe the role of bar and plateau using dynamical Lie algebra, so the representation of the R distribution of your parameterized quantum circuit. But of course, when you're dealing with noise, you don't have a unitary representation anymore. So essentially, you cannot use this group structure for this transformation. And so what we did, we tried to rework a little bit the role of bar and plateau in the context of noisy quantum circuit. And we changed completely the way approaching the bar and plateau issue using non-negative matrix theory, because in the end, what we want to provide to the community is an understanding about the training of the variational circuit. So what you want to provide is the variance of the loss function. So essentially what was proven for a bar and plateau for some kind of circuit is that the variance vanishes exponentially as a number of qubits, as a number of, in particular, as a number of layers. But we didn't have any kind of mathematical formulation of what is happening for variational quantum circuit in the presence of noise. So we wanted to give you just this complete representation for the unitary contribution and the noise contribution. Okay, so conclusion. Let me just go to this slide. Essentially, I can stay also on this one just to give you again a remark about what I'm trying to convince you at the beginning, so that we have two kind of computation for the moment. What is called NISQ, or noise intermediate quantum device, and fault tolerant quantum devices. So for the NISQ one, we cannot provide any kind of computational or guarantees for advantage. We have a lot of heuristic, a lot of interesting application that can give you some kind of interesting application. While moving on the fault tolerant quantum computing with different kinds of algorithms, we can provide some mathematical guarantees. The problem is that we are in the middle with the technology. And so that's why usually I say that where we are is that we are in the transition between NISQ and what is almost fault tolerant quantum computation. So the idea is that we are going to have what is called logical quantum bit, which can be found in the same qubit that you write in the blackboard, because what you write now on the blackboard is not essentially what you can implement on a real devices. And so for us, really the goal is bridging between near-term and fault tolerant quantum machine learning. And going back to the question of where we should do this on a classical or quantum optimization, sometimes it's really dependent on the application. So for example, we know that the traveling salesman person is MP complete. That's true, of course, that's a theoretical guarantees. But then, for example, you can solve an instance of 85,000 cities with the classical computation. So for us that we want to give answer and tool to the community to solve, for example, energy physics problem, we should care about all of different implications. So we cannot work only on theoretical guarantees for potential algorithms. We have to understand, according to the dimensionality of our problem, what is really the right solution that can be implemented today. So this is a kind of the way to do this. And that's why we want to make comparison of computational costs in a different way, considering different aspects. If you talk with theoretical people, of course, everyone is interested in exponential advantage, but those are not something practical that you can obtain now. If you want to bet on something in terms of QML, I think that the part on quantum generative model is something that can give you very interesting result, and this is something we are currently working a lot in our field. Okay, so with that, I just want to thank you everyone for your attention. If you have any questions.
Your quantum must be 3-dimensional or can be 1,000-dimensional.
Quantum can be?
Your quantum is sphere with X, Y, Z. It's 3-dimension. Is it fixed to 3-dimension or it can be
in the representation?
Yes.
The block sphere.
Yes.
Okay. No, this is a graphical representation. So quantum H qubit is defined in C2, and then you have the block sphere, which is the kind of transformation to R3 that for 1 qubit works that give you a graphical representation. But if you already work with 2 qubits, you don't have the same kind of geometric representation of it, but essentially it scales as C2 tensor, the dimension of the qubit you're working with. Yeah. It's essentially in a complex space. We don't have the real connection. Yes. Yeah. The dimensionality of the problem is given by the number of qubits. Yes. Yes. Yes, that's the map. Yes.
Sorry, so you mentioned quantum generative models.
Yeah.
Do you have models that mimic these diffusion generative machines in classical machine learning?
Yes. So for the generative model, I mean, what the community has done so far is really taking the classical model, put a Q in front, and trying to develop something. So this is what we did for quantum supervector machine. And for the generative model, we have the quantum generative adversarial network. We have a pure quantum model, which is the quantum circuit board machine, the quantum Boltzmann machine. For the diffusion model, there are some ideas about how to do that, but there is no clear way how to do that. Diffusion model, and also people are looking into the way to do normalizing flow in the quantum setting, but this is not something that can be done in a quantum way in the same way as people are doing normalizing flow, because we cannot, we have a reversible computation because of unitary, but because we measure, we cannot have a reversible computation in the end. So this is the bottleneck of the field, because you cannot reverse the measurement operation. Yeah.
Another question was, so you are considering quantum amplitudes that, well, in quantum physics are represented through Feynman path integrals.
Yes.
Are these quantum computer algorithms that you use to look for these amplitudes, are they somewhat related with the path integral that is behind the amplitude?
Yes, there is some formulation for this, in particular quantum computing for condensed matter, but also for theoretical modeling in high energy physics is used to overcome the problem, for example, of Monte Carlo, the sign problem, because you can go in the Hamiltonian formulation directly of this problem, and then you can overcome this problem with weak rotation. So the way one of the most potential direction of quantum computing, also coming back to the very original ideas of quantum computing from Feynman, was really to go into this direction for Monte Carlo simulation. Yes.
Hi. So if I understand you correctly, you said you didn't do backpropagation for the parameters?
No, we don't have this because we cannot store intermediate result of quantum circuit. There are some indication about how this should work, but in practice we cannot do with backpropagation because we cannot save intermediate state of quantum circuit along the progression.
Okay, and so what do you use instead?
So the training is done with the same rule as the rational quantum circuit. So essentially you have a flow from from quantum to classical computer. So you update all the parameters together.
But how do you know how to adapt them? So that's close.
I mean, for example, the calculation of gradients is done, for example, with a rule that is called parameter shift. So essentially, you take a quantum circuit, you take the weight of the gate, and then you apply a shift in the weight so that you can get a finite difference of the gate, and then you can update the gradient according to that. But it's very, very expensive. Very expensive, yes. Indeed, one of the direction of the community is try to avoid the calculation of gradients. And one of the paradigm that we are looking at is also reservoir computing, that for quantum reservoir computing, essentially you encode the problem as a natural Hamiltonian evolution of a system. And then the training is given by the natural time evolution of the system, which is more effectively done on a quantum system with respect to the classical one.